Okay, it's time to start. So, any question from next time? Yeah. So this time we go over this one of the biggest applications of density matrix, that is reduced density matrix. Okay. So we talked about this at the very end of the lecture last time. But this is a very important concept, so I just want to re-emphasize. Okay, so reduced density matrix is something that will give you density matrix. Okay, so this is the stories are usually when you have a composite system and your systems might be entangled. Okay, so say if you have a two-part system, so you have a part A and a part B, and then the A and B can be far away from each other, but they have this weird quantum entanglement, giving them some kind of quantum correlation between them. And so A and B are far away from each other, and so the important thing here is you want to know what happens when A and B do things locally. Okay, and well, so A and B share this quantum system. They give you some correlation, and we want to see that. So if you put the A and B system together, then you can think of this just as a big space, and then you can do the usual unitary and everything on this entangled state. But we want to study basically the property of entanglement, and so we want to see what A or B can do locally. Okay. And so turns out that if they share an entangled state, then we can describe whatever they can do locally by this density matrix formulation, and we can just calculate a density matrix on A and density matrix on B. Okay, and so I guess let me write a little more. It's here. Sorry. Yeah, let me write a little more. So the idea will be that so A and B share some entangled state rho AB, and I guess a big part of the entangled state, and by definition of this state being entangled, is not a tensor product of two things. So one funny thing happens is that if you just put this rho A and rho B together, so you think about rho A tensor rho B, then it's not going to be equal to your starting state rho AB, because this is an entangled state, it's not a tensor product of two states. Okay, if this is entangled. Okay, and yeah, so they have some correlation that you can only see when you put the two things together. Okay, and so this is reduced density matrix, and back to a bit of moments. So we can calculate the reduced density matrix by this partial trace operator here. So suppose we want to see the reduced density matrix on system A, then we trace out part B, and the trace out part B is really like a trace. Okay, so we define it by these two rules. So if you put a trace on this on this tensor state that are all very simple, so it's AK to A bra tensors BK to B bra, then you just get rid of B part and replace it with a trace, or you put a trace on B part, and the trace is just a number, so this is just a matrix on the register A. Okay, so on the register A it still stays at this K to A1 bra A2 matrix, and then multiply by the trace of the B part, which is B2 inner product with B1. Okay. And those are only defined, this operation is only defined on very small subset of matrices on this HA tensor HB, but we can extend this to every possible matrices on this HA tensor HB by just using linearity. So we say trace B of any state or any density matrix rho AB plus any density matrix sigma AB equal to trace B of rho AB plus trace B of rho sigma AB. Okay. So this is the definition of partial trace. Okay. And yeah, as we said, so partial trace give you maps the density matrix on HA tensor HB to a density matrix on HA. Okay. because the B part I get traced out. Okay. And we see an example. So you do partial trace, partial trace on this beta 00, this EPR pair state. Then we get a totally mixed state as the as a reduced matrix on A. And then here is an example of what we say here. So the rho A tensor rho B now equal to rho AB. So because you can see that, so rho A equal to this 1/2 identity, and because A part and B part are basically symmetric here, so it's very easy to see that rho B also equal to 1/2 identity. So this should be B here. Okay. So rho B also equal to 1/2 identity. So rho A tensor rho B will equal to 1/4, and still identity tensor identity is a bigger identity on 4 dimension. Okay. So you see rho A tensor rho B is this identity on 4 dimension, and so this is like 1/4, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Okay, and that's different from this state here. This state is 0, 0, 0, 0, and 0, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1. It's different from this matrix here. Okay, yeah. So reduced density matrix, you get local terms, but each local term together is not same as usually not same as global density matrix. Okay, and yeah, and we give this kind of physics proof that reduced density matrix will give you the same measurement outcome. So we say this is a bit of convoluted proof where we use this physical reasoning, says that your A part and B part are really far away, and whatever you do on B part shouldn't affect what you do on A part. So we might as well just do a computational basis measurement on B part, and the computational basis measurement on B part, they will have measurement operator of identity on A part and the projection on computational basis. And then we can see that the post-measurement state times the post-measurement state are probability. So I want to calculate this M rho AB M dagger, and this is M and rho AB M dagger. And then essentially you use a bit of calculation, you can show that, well, that is on B part. On B part you just left with whatever you do, you left with this K die here and this bra I here, because this is this is the leftmost element on B part and this is the rightmost element on B part. And so on B part you are just left with this K die bra I, and the other part will be multiplying on this rho AB. And so you see that this operator is basically just a number on B part, because on A part is something, on B part is this dimension 1 and dimension 1 star, right? So this is, on B part is a row vector here multiplied by something and then multiplied by a column vector. And so on B part this thing is dimension 1. So this is basically some matrix in A part and there is some matrix in B part. Okay. And and by our rule of measurement, the post-measurement state, by our post-measurement state of density matrix, we say so a lot of slides before we say that the post-measurement state should be summation I and mi rho mi dagger, and so here, so this thing here is our mi rho mi dagger, so we just sum over I, and so we have sum over I, and excuse me, yeah, and sorry, and yeah, so our state is this thing sum over I, but if we throw away the B part, so yeah, so if we throw away the B part, then A part is just somewhere I of those things, and you see that this is basically doing trace on B part, okay? Because another way to say in trace is you have this sandwich between all the computational bases and sum over them. Okay, And so that's a small review on reduced density matrix. Any question? If not, if not, then let's go to other slide, and we kind of want to see. Okay, let's keep this, and let's go to next slide, and we're going to talk about purification and Schmidt decomposition. There are two ideas. That's excuse me. Let me adjust this. Okay, yeah, back. Yeah, so we are going to talk about two ideas that's very related to, very related to reduced density matrix. Okay, and the first one is the Schmidt decomposition. Okay, and I guess it's a way to characterize your relationship between your reduced density matrix and reduced density matrix and your starting entangled state. Okay, and the setup, but it's a more special case because it is only defined on a pure state. Okay, and although we say we define the reduced density matrix on a general mixed state, but a lot of time you will have a pure state between your two systems. Okay, and yeah. So I should say, okay, so there are two important things here, and the second one we didn't say. Okay, so the first one is so setup. First, you have a pure state between your two systems. So you have some system A and some system B. Okay, first one is a pure state, and the second one is that you only have two systems. Okay, and so it's bipartite. Bipartite. Okay. So the first important thing, we only consider the state as pure. Second important thing, we only consider system that only have two components. Okay. And we find out that then there is a good way to write down this pure state that will tell us a lot about the entanglement between A and B. Okay. And it's in this form. Okay. So we find out that we can find some basis IA on system A. Okay, sorry, not basis. They are set of orthonormal states, orthonormal states IA on system A, and orthonormal states IB on system B, such that psi equal to summation over I lambda I and IA tensor IB. Okay. And what's interesting about this form is that there is only one I here. This is only one summation. Okay, and yeah, because so let's jump ahead a little bit, because if you write so later when we do proof, we'll say, well, because if you just have whatever orthonormal basis on A, whatever orthonormal basis on B, then obviously you can always write your psi as a linear combination of is J tensor K element, but you see that here we have two dummy variables to be summed over. Okay, so if you just pick arbitrary orthonormal basis on A and B and try to write psi equal to decomposition of J tensor K, then you will need to sum over J, then sum over K, and have coefficient AJK. But for Schmidt decomposition, here this I and AB, you only need to sum over them once. Okay, so this is going to be like 1, 1, 2, 2, 3, 3, 4, 4. So you don't have cross terms, you only have one index here. Okay, so this is a very special decomposition, and also there are special property on those lambda I. So those lambda i's are going to, you can pick them to be non-negative. Okay. And I guess non-negative is not too surprising, because non-negative is real, because whatever phase it has, you can just absorb it into IA. So it's pretty trivial, you can get that this is non-negative. But people like to define that non-negative. So it's a cleaner form. And also, then there's something that's less trivial to be true. That is summation I, those lambda I squared equal to 1. Okay. And anyway, those lambda I are called Schmidt coefficients. Okay. And any question about the definition of Schmidt decomposition? And this is really a theorem here. The theorem is saying that any pure state on bipartite system can be written in this way. Okay. And I guess, did we say? So the theorem here is that, so this is really a theorem here. So theorem is that if you have any pure state on any bipartite system, then it has this Schmidt decomposition. And I guess a bit of trick here is that this IA and IB depend on your side here. Okay, so this is our Schmidt decomposition. It's this form. And let's first see some consequences on Schmidt decomposition. Okay, and first, the consequence of Schmidt decomposition is that we see rho A and rho B are the same if you pick the basis pick the basis for A and B that contains your IA and IB. Okay. So here I need to say these things a bit weird because this IA, although we call it the Schmidt basis, but sometimes the number here doesn't actually match the dimension of the system. It might have fewer states than the number of might have fewer states than the dimension here, and the same for IB. And so it's a bit weird to call them bases, but I guess for simplicity, we'll call I and IB bases, although they might be just a subset of a basis. Okay, and anyway, let's pretend they are bases. And so if we use IA as a basis for A and IB as a basis for B, then we see that. Then we see that the density matrix for A and the density matrix for B are the same, because density matrix of A is you trace over B part of your side, and and when you trace B part, then you need so when you trace the B part, then you need this IB equal to. So it's a little so this is psi, ket, psi bra. You will have two summation. There is a summation I and summation j, and so you have lambda I, lambda j, and IA, IB, and JA, JB. Okay, so there will be a I for this ket one part and a j for this bra part. And and I have a small typo here. Okay, and so when you trace over the B part, you will have inner product between IB and the JB. So you will see that I need to equal to J, and so I equal to J. So you just have this lambda I squared IA. And similarly, when you trace over the B part, you also get I need to equal to J. So you have this lambda I squared IB. Okay. And so if you pick this IA as a computational basis, IB as computational basis, or part of computational basis, then you see that rho A equal to rho B. Okay. And that's if you pick the same basis. If you don't pick the same basis, you still see the eigenvalues are the same. Okay. And so rho and rho B always have the same eigenvalues. Okay. And a lot of properties of the reduced density matrix depend on the eigenvalues. So you see that on a pure composite system, pure state of pure entangled state over a composite system, a lot of property on system A and a lot of property on system B are the same. Okay. So that's one consequence of Schmidt decomposition, and that's the first step. Then let's go to the proof of Schmidt decomposition. And the first step of the proof we already done. So we just want to parameterize an arbitrary pure state between C7 and C7b. And yeah, so we have an arbitrary state here, arbitrary pure state here. And so we just give two orthogonal bases on C7 and C7b. Okay? So we write this psi as sum over all possible linear combination of these orthogonal bases between over both C7a and b, such as J tensor k. Okay? So summation Jk over whatever coefficient here, and the basis state J tensor k. Okay? And then we just use this big step, and basically we are done. Okay? And what we use is what we call singular value decomposition. Okay? This is so basically offload or proof to this singular value decomposition theorem. It's a very powerful theorem. Says that, okay, and this is something that very useful, and you better remember even if you don't. This is something that you should learn in linear algebra, and if you don't, you should memorize now. You should. It says that so for whatever matrix A, and this don't even need to be a square matrix, so it can be a matrix of in dimension m and n, and then you can write it into singular value decomposition, and I think it's you can write it as a n by n matrix. You can write it as a n by n matrix U, and n by n diagonal matrix, so you have diagonals here, and those are called singular value, and this is D, and then you have n by n matrix V here, okay? V here is n by n, okay? So any matrix A, you don't need to have any restriction, don't need to be normal, nothing. Whatever matrix, complex matrix A, you can write as a product of three matrix U dV. And so U and V are going to be unitary matrices. They might have different dimensions depending on whether m equal to n. And D is a diagonal matrix, and the diagonal means that it's diagonal here and all zero here. So if m doesn't equal to n, you have a lot of zero here. But anyway, those diagonals are called singular values, and the diagonals are going to be positive, or you can pick them. People will pick them to be sorry, not positive, non-negative number. Okay, so it's you have D here, and so if you write this matrix multiplication A equal to U dV element-wise, then you will have the JK's element is UJI DII summation I, and UJI DII VIK. Okay, so this is just matrix multiplication. But here inside this D, you only need to have one index because D is diagonal. So you just have DI here. So your summation I, so this is summation I on these two, and this I will be matrix multiplication between U and D, and another summation of I between this second I here and the first I here will be multiplication between D and V. Okay, so it's U times V, D, and D times V. And anyway, so the singular value decomposition, this is very important even outside of quantum computation. So hopefully people remember that. But let's go back to quantum computation. So we have singular value decomposition, and as we say, so we put the matrix A equal to this U matrix times D matrix times V matrix, and element-wise, this means that the JK's element is sum over I, and UJI DII VIK. Okay. And we still have a summation JK, so everything's still here. Summation JK and the J here, K here. Okay. And summation J, UI, JJ, and the summation K, VI, KK. Okay. And then then also rename this DI equal to lambda I. And okay, so what happened is you see that this is a state that depends on I, and you can call it IA. this is a state that only depends on I, you can call it IB, and obviously this is a number that only depends on I, you call it lambda I. And then we get our form of our streaming decomposition. So this is summation I, lambda I, and IB. Okay. And but our proof is not done, so now we need to use a few properties to justify this streaming decomposition. Okay. And so first thing I guess I didn't type here is that those lambda I are non-negative because we say in singular value decomposition, singular values are non-negative. And we also need to check that the set IA and the set IB are also normal to each other. And that use that the U and the V are unitary. And J and K are also normal. So J and K are computational basis, and so you have a basis multiplied by a unitary, that's basically a changeable basis, and so you still get also normal basis. Okay, and but it's not quite basis, so you have also normal elements and times the unitary, because the unitary preserve inner product, so those things are still also normal. And similarly, you have also normal element, also normal vectors here, and then you times the unitary matrix, and this is still also normal. Okay, and yeah, so we see I and IB are also normal set, and that shows that psi has whatever pure state psi always has this streaming decomposition. Okay, any question? And we also have a bit of a uniqueness of streaming decomposition, and this we don't have proof here, but they just stay here. And basically because this is basically saying that comes from singular value decomposition is is almost unique. Okay, so what do we mean by almost unique is that you will have so-called singular vectors and the singular values. Okay, it's so singular value decomposition is a bit like eigenvalue decomposition, and you will have left singular vector and the right singular vectors corresponding to your singular values. So those diagonals are singular values, and if you have unique singular vectors, then you corresponding to you have unique I and IB. So most of the time they are unique, but sometimes you will have sometimes they are not unique because lambda I might be degenerate. That means that you might have some lambda I equal to lambda j, and just like the eigenvectors. So remember, when we talk about eigenvectors, we say eigenvector decomposition may have degeneracy. Say your matrix look like this, and you have an infinite choice of eigenvectors for this matrix because the two-dimensional space is degenerate. Okay, and yeah, so similar things will happen in singular value decomposition. So if you have degenerate singular values, then your singular vectors are not unique, and then you have some freedom in choosing your I and IB. Okay, so that's Schmidt decomposition. Okay, and let's have a bit more terminology. Okay, so terminology, first one is something a bit funny. So we call this set of orthonormal vectors I and set of orthonormal vectors IB are the Schmidt basis, because they are really like orthonormal basis for system A and B, but they might be not actually a basis because the number of them might be less than the number of the number of them might be less than the dimension of your space. But yeah, but it's still easier to call the Schmidt basis than calling the Schmidt subset of basis. Okay, and yeah, then the next terminology we already talked about is Schmidt coefficient. Okay. So those lambda i's, those numbers, we call them Schmidt coefficients. And then we have a funny, I guess not really funny, but another concept that we haven't talked about that's called a Schmidt number. That's just the number of non-zero lambda I. Okay, this is a Schmidt number. So lambda I can, well, yeah. So lambda I are a lot of number that's non-negative, and but non-negative number can be 0, and we want to see how many non-zero lambda are there. And this is called a Schmidt number. And the Schmidt number will be a little bit related to how entangled the state is. And yeah, we will see here. Okay. And here is the motivation of Schmidt decomposition is, well, it will tell us how entangled the state is, okay? Because the Schmidt coefficients are very related to how entangled the state is, okay? And so first, the justification of why is this tell us how entangled it is because Schmidt coefficients are preserved under local operation. That means unitary transformation on system A or system B. Okay, so we should say. So the logic here. So the logic here is a bit of convoluted. So once again, we have A and B. They share some entangled state, and this some pure entangled state side here. And we want to see how entangled it is. And we know entanglement is a global property. So entanglement is something you can only tell when you have only both part A and part B. And so we kind of do a kind of a reverse logic. So entanglement is okay. I guess entanglement is global, right? I guess I just write global. Okay. So entanglement should be a global property that you can only tell when you have both part A and part B. And that means that it's a global property that is not a local property. So we think entanglement should be a property that you cannot change by only doing local operation. Okay, and yeah. So let's see what happens when you do local operation. And we see that the Schmidt coefficient is something that. So the Schmidt coefficient is something that don't change by local operation. Okay. So entanglement is something that can only change or can only be created or destroyed by global operation. Okay. And we see that Schmidt coefficient has a nice property that they don't change by local operation, because if your state side has this Schmidt decomposition summation I, B, then you put unitary A. So say you have a U that's a unitary on system A alone, and then your Schmidt decomposition becomes summation I lambda and UIIB. Okay. And I'm missing a parenthesis here. Okay, and you see that you can write down, you can immediately write down the same Schmidt decomposition. Okay, so not same Schmidt decomposition. Excuse me. So this U side, you can immediately write down its Schmidt decomposition, and you see that it has the same Schmidt coefficient lambda here. And the only thing change is you change your A basis from IA to UIA. Okay? Because U is unitary, so UIs are also no basis. And so this is the Schmidt decomposition. Those lambdas are positive numbers, non-negative numbers, and these UIs are also normal states, and IB are also normal states. Yeah. So you can immediately write down a Schmidt decomposition here, and you see this Schmidt decomposition has the same coefficient as this Schmidt decomposition. So same lambda I here, same lambda I here. And so Schmidt coefficient doesn't change when you put the local unitary. And yeah, similarly you put U on B, then you only change this IB to UIB. Okay? And okay, so that's the invariant of a Schmidt coefficient on the local unitary. And so we keep saying that Schmidt coefficient can tell us how entangled the state is. And so there are actually mathematical formula to calculate some quantity, some single number of entanglement, and between A and B from the Schmidt coefficients, but it's a little too details, and here we only give a very general qualification of relationship between Schmidt coefficient and the entanglement, and that is we say that if the distribution, so we should say, so we have a whole bunch of number Schmidt coefficient here, lambda I, distribution, and so if those numbers are spread out, then if they are more spread out, it's more entangled, and if they are more concentrated, then the states are more pure. And so here we have a very very extreme example. So what I mean by concentrated means that, so remember those lambda they are a bit like a probability, okay? Those lambda I satisfy that their summation square equal to 1, okay? So you can, and they are non-negative. So you can think of them as the square root of probabilities, okay? And basically, if the probability are concentrated on 1 over the I, then it's very concentrated, okay? Okay, and yeah. So one thing we're going to see in more detail is that lambda I is like a square root of probability. And anyway, so the most concentrated, because they need to be squared down to 1, and so the most concentrated case of the Schmidt coefficient is 1, 0, 0, 0, 0, 0, 0. Okay, so one of them is 1 and all other 0. Okay, and you can prove that if this is the case, then the state is a product state. So that means the state is not entangled between A and B. And I guess one of the proof is very simple. So if this is true, so this direction is very simple. So if this is true, then you see the state is just, you get a Schmidt decomposition, and you only need to sum over one of them because there is only lambda 1 equal to 1. So if that is the case, then psi just equal to lambda 1 and 1a tensor 1b, and yeah. And this is obviously a product state is just this 1a tensor 1b. Okay, and you can prove that the other direction is also true. So if it's a if it's a product state, then it's a Schmidt coefficient is this thing. Okay. And also this gives us the meaning of a string number. Okay, so we see the string number is 1, then the state is a product state. Okay. Yeah, so this is just by the definition of Schmidt number. Okay. String number is the number of non-zero lambda I. Okay. And here the number of non-zero lambda I is 1. Okay. And yeah, so one way to state that whether a state is real or not is check its string number. Okay. And so we see that so we have a kind of idea that if the string number is larger, then the coefficients are more spread out and the states are more entangled. Okay. Yeah. But string number is I want to say very unstable way to characterize the entanglement, and when people actually want to try to calculate the number for entanglement, they don't use string number. Okay. But that's outside of the scope. But string number is good to tell that whether a state is a product state or not, because yeah, if it's 1, your string number is 1 if only if the state is a product state. Okay. And here we give some bound on string number. So string number is the number of lambda I that's not equal to 0. And then this is less than the number of I and IB here. And but we know I and IB are also normal set inside C sum A or C sum B. And so number of solar elements cannot be more than the dimension of your system. So we know this number I and number IB is less than the dimension of C sum A and the dimension of C sum B. And also if string the whole integer, you see that Schmidt number is upper bounded by the dimension of system A or dimension of system B. Okay, and yeah, that's the Schmidt number. It's some kind of characterization of the entanglement between two systems. Any question? And we have 10 minutes left, so I guess now go to purification. Let's give a bit of an example of Schmidt decomposition. Okay, and yeah, so we have 3 states here that we want to write down the Schmidt decomposition, and I guess it turns out that we already have a Schmidt decomposition here. Okay, so the 3 states are our favorite EPR pair, square root 2, 0, 0, plus 1, 1. Okay, and so this state is already in Schmidt decomposition, and let's write down things. Okay, so we have lambda I equal to this 1 over square root 2. Okay, so lambda I are 1 over square root 2 and 1 over square root 2. And we have our IA equal to 0 and 1, and IB equal to 0 and 1. Okay, and then the Schmidt number equal to 2 because you have a 2 non-zero number here. Okay, and yeah, so this is 1 over square root 2, 0 tensor 0 here, plus 1 over square root 2, 1 tensor 1. So this is already in Schmidt decomposition. And yeah, from here you see the eigenvalue of density matrices. So we have this calculation here, right? So we see the eigenvalues of the density matrices are lambda I squared. And so you know the reduced density matrices will have eigenvalues 1/2 and 1/2. Okay, and then the second one is a similar state. Okay, so 1 over square root 2 plus tensor plus, then plus 0 minus tensor minus. Okay, and so you see that this is also in Schmidt decomposition already, but this is in Schmidt decomposition already. Just that the IA becomes this plus and minus, and IB becomes this plus and minus. Okay, and so but I want to show a little bit of why Schmidt decomposition is cool. Okay, and but this is only in Schmidt decomposition, but you can think about this state in computational basis. Okay, so if we put this state in computational basis, is 1 over, let's see, 2 square root 2, and so you have this. I guess this is a set. Okay, this is a funny example. Sorry. Yeah, this is not too interesting. And here, I guess in computational basis, then you will see that we will see the degeneracy of Schmidt decomposition. Okay, because then this plus is 0 0 plus 0 1 plus 1 0 plus 1 1, and this minus is 0 0 minus 0 1 minus 1 0 minus 1 plus 1 1, and so this cancel out, and you have 2 here, cancel the 2, and this is actually same as the previous state. So this is 1 over 2 0 0 plus 1 1. Okay, and here you see that Schmidt decomposition, and this IA and IB part might not be unique, because that's what happens when you have a degeneracy in your lambda I. So that's because this is 1 over square root 2, same as this is 1 over square root 2. So you actually have a bit of freedom in choosing a basis element to be 0, 1 or plus minus here. Okay. And the next one is this plus state. And so here, once again, it's already in Schmidt decomposition, and it has lambda I equal to 1. So usually it's a product state here, so I only have one lambda I. So here lambda I equal to, I like to write it as 1 and 0. Okay. I guess that's just write 1 because we didn't say we want to have a maximum. Okay. Lambda I just 1. And then IA equal to plus state, and IB equal to the plus state. Okay, and you see this pure state. Oh, sorry, this is obviously a pure state. This is a product state because lambda I equal to just 1, and then it's a product between plus and a plus. And but I guess but the next example, let's do kind of this thing. The next example shows the usefulness of Schmidt decomposition, because if you put it in the computational basis, then it's 1/2 is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 state, and so if you put it into computational basis, it's this quite complicated form. And if you look at this state in this form, it's not easy to see whether it's entangled or not. You can ask yourself, is it entangled? Okay. And so previously you might not know whether this is entangled or not, but now you know that you can calculate the Schmidt decomposition of this state, and then you will see that it is actually the plus state times the plus state, and this is the product state. Okay, so this state is actually not entangled, but this state is entangled, something like that. Okay, and so that's Schmidt decomposition. It let us test the entanglement of a pure state between bipartite systems. Any question? We have 2 minutes left. Actually, only 1 minute left now, and I guess obviously we cannot finish purification, but I just want to give a small marketing on purification. So purification is also related to the reduced density matrix idea, and it's like a reverse of getting reduced density matrix. So remember, we said reduced density matrix is you get, so let's jump ahead a little bit. So if you have entangled state on system AB, might not be pure, but let's pretend it's pure for now. Okay, so you have an entangled pure state on system AB. You can do system AR, and you can do partial traces on system R and get a reduced density matrix on system A. Okay, this is a density matrix OA. And purification is kind of a reverse of this partial trace operation. That is, you are given some density matrix OA, then you want to find some pure state on system AR. That when you do partial trace, you will get system OA. You will get this reduced density matrix OA. Okay, and that's the idea, and we'll see how it can be done tomorrow on Thursday, if the weather allows us to do class on Thursday. Okay, yeah. So yeah, not sure whether we are going to see on Thursday, but we'll talk about purification and some classical computation next time. Okay, so yeah, see you on next class.